This video is going to be on momentum and impulse graphs. So the type of graphs we might see in an impulse momentum type question. So the first graph that we might be looking at is a force versus time graph. Okay. And since forces are a vector, we want to make sure that we have both positive and negative axes. So a positive force just means it's pushing rightward. Negative force just means it's pushing leftward. Okay. And then we got time in seconds on the x-axis. So we might have a force versus time graph that looks something like this. Okay. Now, force versus time graphs give us a lot of information. So remember, when we want to figure out what a graph can tell us, it's a good idea to use TSA. So T is the title, so we're force versus time. S is the slope, which is change in y over change in x, so force over time, which if we think newtons over seconds, that doesn't really mean anything. So that's going to be a big old nothing for us. Okay. And then area. So areas are usually going to be a change in y times a change in x. So force times time, or if we're thinking units, a newton times a second, which, if you remember, is impulse or change in momentum. So if we want to know information about the impulse or the change in momentum, we can use the area. Now, the reason that's exciting is because if we know the mass, so let's say the mass is known, then we can take that area calculation, which again is our change in momentum, and figure out information about the change in velocity. Okay. So when I say area, I mean area between the graph and the x-axis. So here's the x-axis. So we're kind of taking the area that's bounded between the graph and that thick line. So we're going to have an area up here, and then an area down here. Notice how I'm starting and stopping at the x-axis. I'm not crossing the x-axis with the highlighter at all. To calculate that area, what we're going to want to do is break up the area into shapes. So here I see a rectangle and a triangle. Oops, that's not how you spell triangle. And then down here, same thing. I have another smaller triangle and another rectangle. So as a reminder, the area for a rectangle is base times height. Area for a triangle is 1/2 base times height. So these two areas up here would be considered positive areas. Okay. So in these areas where we have positive areas, that's going to mean that our momentum, okay, and that's going to be assuming our initial momentum of 0 or positive. Momentum is going to be increasing in that section, okay, which means we're also going to have increasing velocity. Okay, so even in this section here where the force starts to decrease, we're still going to have increasing momentum because our area is positive. And then here in this bottom section, that's considered negative area, so negative impulse, which means in that section our momentum is going to be decreasing. Okay. And if the positive area equals the negative area, then we have a total change in momentum of 0. Okay. So one thing I forgot to say is where our momentum is decreasing, that is likely where we are slowing down. And if that area is large enough in the negative direction, we might actually change directions. Might have a large enough impulse to kind of change our direction. Okay, so that's one type of graph, force versus time graph. The other type of graph that we are going to deal with, if I can get back to my black pen, is momentum versus time. Okay? And again, momentum is a vector, so I'm going to have a positive and a negative axis because these can move backwards and forwards. Okay? So if we have an object with no external net force on it, we expect the momentum to remain constant. So again, constant momentum here means no external force. Okay. Whereas, let me change up the color. If we have a graph that maybe looks something like that, here we have changing momentum. So we do have an external force. Okay. Now it's not a constant external force in that case, and I'll talk about why in a second. Okay. So let me write non-constant external force. Okay. And then one last graph, if I had a graph that looks like this, oops, I need to make it more linear. If I had a graph that looks like this again is changing momentum with an external force. Okay, but this would be a constant external force. And maybe just by looking at the graphs, you're able to figure out why between the two, one has constant external force and one doesn't. But if you're not, let's go ahead and figure out a TSA analysis. So T, tidal, S, slope, A, area. So this is P versus T. Slope is y over x, so momentum over time. So unit-wise, that's a kilogram meter per second over a second, which is the same thing as a kilogram meter per second squared, which you might recognize as a Newton. So that means the slope is going to represent, my pen would write, the force. Now let's say the unit thing freaks you out, okay? So we could remember that change in momentum is force times time. So change in momentum over time is force. So it's another way to get it that the slope gives us force. Area is momentum times time, or a kilogram meter per second times a second, which is just a kilogram meter, which is nothing. Yay, nothing. Okay, so going back to how did I know that the forces were constant or not constant? Well, I looked at the slope. For the blue line, my slope is changing. And if my slope is changing, that means my force is changing. Whereas the red line, the slope is constant, which means my force is constant. That even works with the black line. The slope is 0, so my force is 0, which makes sense because I have constant momentum, which means I should have no external force. So the last type of graphs we might expect to see are velocity time graphs. For some reason, my pen's a little funky today. There we go. Okay, velocity meters per second. Sorry guys, I'm not sure what is happening, but it's not writing. So meters per second. Oops. Again, velocity is a vector, so I want to have positive and negative. Okay. Now, the way the AP exam loves to show velocity versus time graphs with momentum is they'll show us the velocity versus time graph for two objects in a collision. So we might have one object whose velocity starts off constant, changes, and then goes back to constant, something like that. And we might have another object whose velocity does something like that. Okay? So this section here is our collision section, and we could actually find time from that. Okay? We could find how long the collision took place, and then the fact that they have the same velocity after the collision tells us that they stick together. Okay? Now, the reason why this thing might be fun is if we knew the masses of both of the vehicles, then we could use the idea that mass times change in velocity is force times time. we can get the change in velocity for one of the objects, not both, just one. So just one, using the mass. So we could rewrite this as m1 delta v1 is force times time. So we can find the change in velocity by just looking at what it is here and what it is there, and then doing v final minus v initial, and divide by the collision time from the graph. Okay. What you might also be asked to do, so again, velocity versus time graph, is you might have a graph that looks like this. Okay, and you might be asked, is momentum conserved? Okay, so again, this area here, where the velocity is changing, that's where our collision is occurring. So the dotted line changes direction, the solid line changes direction. So we would essentially be plugging into m1v1 plus m2v2 and figuring out, does it equal m1v1 prime plus m2v2 prime? They could also ask us this question with a momentum versus time graph. And that one would actually be a little bit easier because we wouldn't have to do the whole equation. We would just have to add the momentums before together, right? So we could do this in a way that makes sense. We could add up these two momentums to get P initial, and then we could add up these two momentums to get P final, and we could figure out if momentum is conserved by just comparing those two. I'm trying to get my black pen back. There we go. So we would think, are they equal? Is momentum conserved? And if it's not, then we could figure out the change in momentum by doing P final minus P initial. Figuring out, well, so momentum isn't conserved. How much did we gain or did we lose? And from that, you could figure out a whole bunch of fun stuff. Okay. So that is the end of that video.